Okay, everyone, let's do question 6 from the June 2021 CSEC Physics Paper 2. So, radium-226 is radioactive and is represented by the nuclide 22688Ra. So for part A, we are asked that for a neutral atom, so if we have a neutral atom, and in a neutral atom, we know that the number of protons and the number of electrons are equal, right? That's important. So if we have a neutral atom of radium-226, which has these this nuclide symbol, state 1, the number of protons. So we know the number of protons is the same as the atomic number, which is this one here. So that's 88. That's our proton number. So we just simply write that here. And then for part 2, the number of neutrons that are in that neutral radium atom. So we know that the number of neutrons is the mass number minus the atomic number, right? And that's what tells us how many neutrons there are, because we know that the mass number, right, is equal to the number of protons and neutrons that are in the nucleus of that atom, right? So if we know mass number and we want to find number of neutrons, we simply just arrange this so that we get the number of neutrons on one side, right? So mass number minus the number of protons is going to give us our number of neutrons, and so that's what we did here. Actually, this mass number here is 226, so this should be what? This should be 226, right? Minus 88. And so what would we get in that case? Let's see. 226 minus 88, so that would be 138. So I miswrote the 222 here, but it's 226 because that's our mass number, and then we minus 88 from that, right? And we get 138. That's our number of neutrons. Again, this is our little formula here that we rearrange. Mass number is proton plus neutron, right? So our mass number minus the number of protons will get us our neutron number. And so that's what we did here. And we got 138, okay? All right. So the number of electrons now, because this is a neutral atom, which they stated up top, and we know that for a neutral atom, the number of protons is equal to the number of electrons, and we already had determined that the number of protons was 88 from up here, so we just simply put that back down here, right? Number of protons and number of electrons are equal for a neutral atom, okay? All right, so let's go down to part B. So part B says that a radium-226 nucleus decays by alpha particle emission to a radon nucleus, right? So this is the symbol of radon, and radium was what? Ra, right? So radium was Ra, so we're going from Ra-226, and it's been decayed by alpha emission to get us to this radon nucleus, okay? All right. So explain, part I is saying, explain what is meant by the term radioactivity. What do we mean when we said that something is radioactive, right? So the way I've explained it here is that radioactivity is the spontaneous, this is key, it's a spontaneous event, so it's the spontaneous disintegration or decay of an unstable atomic nuclei. So these are key terms, right? Not every atom will undergo radioactivity or will be radioactive. It's only the ones that have unstable atomic nuclei, and this is a spontaneous event. So those are two phrases that you want to make sure that you include in your definition of radioactivity at all times, right? It's a spontaneous disintegration of unstable atomic nuclei. Okay? So I've added a little bit more detail here to say that the nuclei, is unstable because there are insufficient protons to hold the neutrons together in the nucleus, right? So that's the source of instability in these radioactive or radioisotopes, right? The nucleus becomes stable by emitting either an alpha particle, a beta particle, or gamma rays. So that's how this unstable nuclei gets to a place where it's like, it's okay now, it's stable, right? And in order to get there, the unstable nuclei will spontaneously disintegrate, emitting either alpha, beta, or gamma particles, right? And so in this particular case, for this question, if we go back up to here, it's saying that a radium-226 nuclei, right? We can then assume that that's an unstable nuclei, right? Since it decays by alpha emission to give us a completely different element, right? So that's how we would think about radioactivity holistically. It's a spontaneous process, and it happens in unstable nuclei, right? Whenever they're unstable atomic nuclei, what the unstable atomic nuclei does is it gives off either alpha, beta, or gamma rays, and as a result of that, it becomes more stable, right? All right, so that's all for 3 marks. If we captured all of this, we'll be good, right? For our entire 3 marks. So moving down, for part 2, it's asking us to complete the equation for the decay of radium-226, right? So they told us that the radium-226 decays to radon, and it also emits an alpha particle, right? So whenever there's alpha particle emission from our parent nuclide, which is what this one is, this is what we're starting with, the mass number is going to decrease by 4. So that's how we end up with this 222 up here, and the atomic number is going to decrease by 2. So we end up with 86 here. So we end up with 222, 86 Rn. That's our new daughter, if you would like, daughter nuclide. And then the 4,2 alpha that got emitted, right? So this is our equation. This is how we would write that decay of radium-226 by alpha emission, right? So that's what we do for here, and we get our 2 marks, we're good to go. But the key thing is to remember, right, that whenever there's alpha emission, we're always gonna decrease our mass number, which is A, by 4, and we're gonna decrease our mass number by 4, and we're gonna decrease our atomic number by 2. So that's what we did to get from here to here, right? 226 minus 4, 88 minus 2, and that's how we end up getting this particular identity, right? And of course, we write our alpha next to it as well. All right, so moving along to part C. So part C says that radium-226 has a half-life of 1600 years. So define the term half-life. Half-life is the time taken for a mass or activity of a radioisotope sample to decay to half of its initial value, right? So if I have a set amount of radium, if I have 10 grams of radium, it's gonna take me 1600 years, right, to get to 5 grams. That's half of it, right? So that's what the half-life literally represents. It's like, how long does it take my sample to decrease by a half? In this case, they're telling us it's 1600 years. So if I have 10 grams of radium and I wait 1600 years, I'll end up with 5 grams of it, okay? Because that's the half-life. So that's how we define the half-life. For 2 marks, we're good, right? The time takes to decay to half of its initial value. We're good there. Okay, so let's move down to part 2 of that question. So part 2 of this question says that at a certain time, right, at a certain point in time, so we can just take that as our initial time or starting time, t is equal to 0, right? We have a sample that contains 8.0 times 10 to the 8 radium nuclei. So that's our radium-226, right? That's what we started with initially. And they're asking us to calculate the number of alpha particles emitted by the radium nuclei in the next 4,800 years, right? So remember from up here, the half-life is 1600 years. So the t-half or the half-life is 1600 years. And they're asking us at a time t-final, which is 400 years later, right? How many alpha particles would have been emitted by the radium nuclei? So we come over here, you follow me over here, right? the amount of radium nuclei that's going to get decayed over that period of time is exactly equal to the amount of alpha particles that will be emitted by that radium nuclei, right? Remember now, the radium nuclei is decaying by alpha emission. So if there's any amount of it that gets decayed, right, that's because that same exact amount of alpha particles were emitted by that nuclei, right? So this is the key thing that I want to point to here as we approach this question. Let's just circle this. I'm going to box this so that we know that this is our point of, you know, this is what we are working with, this knowledge that if I know the amount of radium nuclei that was decayed, then I automatically know the amount of alpha particles that were emitted by that nuclei, since those two events are connected, right? So let's go back over here now. So they told us the final point in time that we're concerned with. Okay, the next 4,800 years, right? So if I know that the half-life is 1,600 years, what I want to do first is find out how many half-lives would I have gone through by the time I get to the 4,800 years, right? And so to do that, what we do here is just divide our endpoint, so the endpoint that we want to end up by the half-life itself, right? And so we do 4,800 divided by 1,600, and we come out with 3. So that means that it's gonna take us 3 half-lives to get to that. We're gonna go through 3 half-lives to get to that 4,800 year mark. Okay? So we're gonna go through a half-life 3 times in that 4,800 years. So if we're starting with 8.0 times 10 to the 8 radium nuclei, right? Then it kind of is gonna look like this, right? So I'm starting with 8.0 times 10 to the 8 radium nuclei. I go through 1 half-life. So this is my first T half, right? So I go through 1 half-life. I end up with half of what I started with, which was the 8. So I ended up with 4 here after I gone through 1 half-life, which would be equivalent to just 1,600 years, right? Then I go through a second half-life. And when I go through that second half-life, so second T half, right? I'm gonna end up with half of what I had here after my first half-life. So I'm gonna end up with just 2.0 times 10 to the 8 over here, right? Then I'm gonna go through now my third and final half-life to get to this 4,800 years. And so what I'm gonna then end up with, so this is my third T half that got me to this point, right? So I'm gonna go from now 2 to 1 because I'm half in whatever I had here after the second half-life, right? So I end up with there being 1.0 times 10 to the 8 radium nuclei after, so this is what we have after the 3 half-lives, which is after 400 years, right? So what that means is, because I ended up with this, now I want to know, okay, if I started out with 8 and I ended up with 1, that means that the amount of radium nuclei that decayed was what I started with minus what I ended up with, right? And so that means that 7.0 times 10 to the 8 radium nuclei were decayed. And by that same token, we know that the amount of alpha particle emitted by this radium nuclei was also 7.0 times 10 to the 8. So this is my answer here. This is my answer. 7.0 times 10 to the 8 is the amount of alpha particles that were emitted. And that's the exact same as the amount of radium nuclei that got decayed. Okay? Just make sure that you sit with this one a little bit and really understand what's going on. They're not just simply asking you how much radium nuclei do you have after you've gone through these many years. What they're saying is, no, tell me how many alpha particles would have been emitted over this period of time, right? And to do that, you just have to find out, okay, how much radium nuclei actually got decayed. And that's what we did here. Right, we found how much we would have at the end point, but we were saying, okay, if I ended up with this and I started with this, then this is how much was decayed, and by extension, this is the amount of alpha particles that were also emitted. Okay? So that's that one for 4 marks. And so moving down to part 3, they're asking how much more time will elapse or pass, right, before the number of radium nuclei remaining falls to 0.5 times 10 to the 8. No. Remember now that at the end of this 400 years, what we ended up with was this 1.0 times 10 to the 8 radium nuclei, right? So at the end of the 400 years, so let's write that here. After 4,800 years, right? What we had was 1.0 times 10 to the 8 radium nuclei remaining, right? Because that's literally what we had calculated first in part 2, right? So let me write that up here. So from part 2, right, after 4,800 years, we had 1.0 times 10 to the 8 radium nuclei remaining, right? We know that. That's from part 2. So they're saying, how long is it going to take me to get to 0.5 times 10 to the 8? And what you realize is that that's literally half of this that we had remaining after 4,800 years. So we want to get to, how long is it going to take us to get to 0.5 times 10 to the 8, right? So you said that's literally one more half-life. So if we go through one more half-life, then we'll end up with this 0.5 times 10 to the 8 radium nuclei. So literally what I wrote here, we need one more half-life, which is 1,600 years, to get from this 1.0 times 10 to the 8 where we had stopped here down to 0.5 times 10 to the 8. So I hope that makes sense. And that will bring us to the end of this question. And so definitely feel free to drop a comment down below if this was helpful for you, if there are any lingering questions that you have on this. And definitely like this video, subscribe to this channel, and then I'll see you in the next video. Okay?